Okay. Hello, everyone. Welcome to today's meeting. So we have three presenters today. That is, Robin, Aryan, and Rembek. So, Robin, would you like to go first?
Yeah, sure. I will begin to share my screen now.
Okay.
So can you guys see now?
Yeah.
Okay. Yeah, so I want to first start talking a little bit about a specific application of the convolutional layer is the edge detection. I guess this topic has nothing to do with our research topic, but I made this notes a few weeks ago. I guess it's still interesting to briefly talk about it. So edge detection is a basic image processing technique that helps to find the boundary of object in an image by detecting the sharp changes of the brightness. It has been widely used in many fields, such as finding fingerprints of tumors and self-driving cars. So we were giving an input image as shown on the left, and our goal is to output the edges of this input image, like shown on the right part. So the math behind it is very simple. We will use the image gradient to describe these changes in image. So we will formulate it as the delta I here. We will take the partial derivative of I with respect to x and y. And in practice, we will use some discrete derivative to approximate it. Normally, we use these two kinds of gradient filter. Like D0 is 1 minus 1. We subtract Fn minus 1 from Fn. And D1 is we take the average between this difference. So we can see a practical example in this image. If we have a very simple image as this one, like we have 10 on the left side on the left hand side and 0 on the right hand side, we want to detect the edge of it. So it is simply this vertical line. And we will apply this filter 1, 0, minus 1 to convolute it with our image. And we will get this one. It's 13 in the middle line. So it represents the edge in the middle. And yeah, so if we apply it to real image, we will have this consequence. If we apply the minus 1 1, the transpose of minus 1 1, we will get the horizontal edges of this image. And if we convolute it with minus 1 1, we will get the vertical edges of this image. And in this image, we only have very firm and very solid edges in this image. But in practice, we will have some very furry edges, like the fur of this dog and the grass here. So if we directly apply the gradient filter to it, we'll get some this noise here. It's not what we want. We only want to get the edges between the dog and the grass. So we will first apply the gradient filter to it to kind of get a blur version of this image, and then we apply our gradient filter to it. So you will detect the edge better. So it is all about the edge detection part. So does anyone have any question about it?
I remember one of my undergrad dissertation thesis was about a type of algorithm in machine vision called thinning or skeletonization. So it has two names, skeletonization or thinning. And the basic idea is very similar, but the use case of thinning algorithms is for OCR, or optical character recognition. And the idea is when you handwrite a character, it has a thickness. And so in order to better get the features, like the important features from that image and put it into your OCR model, it's a good idea to reduce the thickness of the character to 1 pixel. And then you would have like the outline of the character, and then you could enter it into your classification model. And that is exactly what thinning or skeletonization algorithm does. There are many methods for that. And my dissertation was proposing an incremental method for learning how to thin in OCR models, which was a lot of fun. Like we had a lot of examples of handwritten characters, and when you showed these images, it just reminded me of the thinning algorithms.
So like I will continue to talk a little bit about the reinforced learning. I guess you guys may have talked a little bit about like the fundamental concept about it, like the agents, elements, the agents, environment, action, state, and reward. So I will like continue it with some math behind this reinforced learning.
Robin.
Yeah.
Actually, we haven't talked about the fundamental concepts in our meeting.
Okay, so like, do you want to talk a little about it since like these notes are made by you? Yeah.
It's okay. You can talk about that. You can extend these child notes, and they are just a very short description of the concept. Yeah.
Okay. So there are some like 5 fundamental elements of the reinforced learning, and like it is listed here, like agent, environment, action, state, and reward. And yeah, so like the agent learns to do repeated interaction with the environment to be successful. And the agent needs to be like learn the interaction between states, action, and subsequent rewards, and determine which action will provide the optimal outcome. Like you can see on this image, so we will have this agent, and we take some action AI here, and it is input to our environment, and we will output the state and and the state and reward, and like it is these two are as input to our agents again, and we will like repeat this procedure over and over until like we get our like final results, what we want in the future. So yeah, like there are some notes about how each elements are like in more detail. And states is a situation in which the agent finds itself. It can be a specific place and moment, a situation returned by the environment, or any future situation. And this includes a set of actions available as well as other considerations such as tools, standards, and rewards. And agent is the entity that executes these actions. For example, a robot deciding on a path to work, or a trader deciding what to buy or sell. And action is the set of all possible moves the agent can make. Agents will choose from a list of possible actions. For example, in a video game, the list might include running right or left, jumping high or low, or crouching or standing still. And the reward is a feedback used to effectively evaluate the agent's action. Can be immediate or delayed. I guess like one more element. So the environment will use information about the agent's current state and action as input, and return the agent's reward. and its next state as output. An example of an environment is the law of physics. To the agent, the environment is a black box. I guess this is like all about the concept here.
Yes. Is there any questions? Or you can move on to the mass behind it part.
Okay. So I will like briefly talk about the mass behind it. It is like reinforced learning itself is a general approach to solve reward-based problem. The building of it is based on the mathematical foundation. We can view it as a sequential decision-making and control problem mathematically. For example, if we drive a car and we counter a crossroad, we need to make decision about whether we want to turn left, turn right, or go straight after the previous decision. And the key ingredient here is the Markov decision process. So what is the Markov process? A Markov process is a tuple, SP, where S is a finite set of states, and P is a state transition probability matrix. So PSS prime represents the probability that if we have state S at T time, and we want to transit into S prime at T plus 1 time. So like what is the probability of this transition? So we also make some constraints on the states here. We mainly make two constraints. First is that this Markov states sequence, the probability of moving to the next state depends only on the present state st and not on the previous state s1 to st minus 1. So we can like formulate it as this mass equation here. So given st plus 1 is independent of s1 to st minus 1. And another constraint we made is like the Markov process time homogeneous. So the probability of transition from S to S prime is independent of the time. So it doesn't matter we make this transition at the beginning or at the end of this process, the probability is still the same. And the Markov decision process have like a few more elements on it. It's still a tuple, but it contains 5 elements. S is still the finite set of the states, but we also consider A is a finite set of actions. And P here is a state transition probability, but it is also conditioned on the action, like what action we take at this T time. And gamma here is like a float number from 0 to 1. It's called a discount factor. We will talk about it later. And this R here is a reward function. And the dynamic of the Markov decision process proceeds as follows. We will start in some state S0 and choose some action A0 in the action set to take. As a result of our choice, the state of the Markov decision process will randomly transit to some successor state S1 drawn from the probability matrix. And then from state S1, we pick another action A1, and again, we will come to some state S2 and so on. And we also defined our return function here, like it's the R here. And like our final goal is to choose action over time so that we could maximize the expected value of the return. And the definition of return is as follows. The return GT is the total discounted reward from the time step T. So GT is like a weighted average of the reward from T plus 1 to T plus infinity. And like gamma here is a discounted factor we defined above. So if gamma is approach 1, it means that we like weight equally of all these reward function. We think that the RT plus 1 is as important as the RT plus infinity. But if like gamma is equal close to 0, we only have one term left. Like we only consider the reward in the next time step. And the value function are mainly two kinds of. They are state value function and action value function that help us to find the optimal policy. In the state value function, we it's the expected return starting from a state S and then following the policy pi. And the action value function, we will also consider the action here, the AT equal to A turn here. So we will in practice, we will use the dynamic programming to help us to help us to compute it more efficiently. But I haven't listed the detail here. But if you are interested, you can visit the reference link in here. It provides a very detailed explanation about how you use dynamic programming to calculate this stuff. So last thing I want to talk about is the limitation of the reinforced learning. In real life application, the state space and action space is very complex, and it is extremely hard to solve the problem with simple policy and value iteration. So normally we will need the help of deep learning to model the environment, the policy, and the value functions. And recently, the deep reinforcement learning enjoys the current state-of-art performance, which utilize the popular neural network. Yeah, so it is the end of my presentation. Does anyone have any question about it?
You're doing great. Thank you.
Thank you. Yeah, so I guess I will stop sharing my screen now.
Okay, thanks, Robin, for your presentation about edge detection and reinforcement learning. That is impressive. So maybe next we can move on to Aryan.
Yeah, I'll start presenting now.
Okay.
Can everyone see it?
Yes.
Okay, so I'm going to be talking about end-to-end learning. End-to-end learning is a system through which we train a more complex learning system, but we reduce all the intermediate to middle steps into one single model. And it's called end-to-end deep learning because that model is specifically a deep neural network. And this single model, the deep neural network, represents the entire target system. And it performs the function of all the intermediate layers that would usually be over there. End-to-end learning is typically, it's used for a lot of things, but two of the most widely applied examples are speech recognition and autonomous driving. In speech recognition, the traditional approach is has a lot of intermediate steps. So it starts with the audio input. Then there's an algorithm called MFCC, which is used for feature extraction. Then it goes on to phoneme detection in the speech, word composition, and then finally we get a text transcript output. And this is very widely used. And researchers have spent many years making each part of this entire process. So for feature extraction, there's a separate algorithm. For phoneme detection, there's something else. But the end-to-end approach, which is more widely in use now, replaces the entire chain in the middle into a single neural network. And it just goes from one end, which is the input, to the other end through the neural network. And using the neural network allows us to just have a single optimization criterion to enhance the system. So all of these extra steps are just bypassed. In autonomous driving, similar to what we do in the speech recognition method, we just replace the intermediate parts with a learning algorithm. So the entire system is a bit more complex than the speech recognition system, which is linear. The autonomous driving system is non-linear. It's a bit more complex. So the camera detects an image and the camera takes an image and then it uses a separate algorithm to detect the car in the front, maybe if there are more cars or trucks or whatever. And at the same time, it also uses a different algorithm to detect pedestrians. And then all that information is fed into planning a path for the car. And that goes into steering the car to take a particular direction for the path. And all of this is really complex. So, and researchers have spent a lot of time designing each individual part of this algorithm, of this entire process. So we can bypass all of that using just a simple learning algorithm. Um, I'm going to talk about the advantages of end-to-end learning. So end-to-end learning lets the data speak. And because this is like a purely machine learning approach, there is the entire process is handled by a machine learning algorithm, a deep learning algorithm. So for a large enough data set, the neural network can figure out everything. So there is no need for any human intervention. There's no need for any extra knowledge to be fed in from our side. The other advantage is that it requires less hand designing of components. So, like I said, in all of these design pipelines, each of the steps is designed by researchers. Um, Researchers have spent quite a few years just designing these systems. Many have built their entire careers on designing these systems. And end-to-end learning bypasses all of that, and it really simplifies the entire workflow and saves a lot of time. And because it's this simple, it would also eventually make adopting these kind of machine learning systems more easy. At the same time, there's a lot of limitations to end-to-end learning. We need a large amount of data. So because this is a purely machine learning thing, uh, it requires the incorporation of a large amount of data. So normally when algorithms are designed individually, we can feed in some of our prior knowledge, and this enhances the performance, and it's normally considered a key element. But when we remove all of that, when there's no human knowledge fed into it from before, the machine learning system relies completely on data. And normally that's good, but for like smaller systems, it's a little harder. So it becomes a little more complicated for smaller systems. It's very difficult to improve or modify the systems, because if you need to make a structural change or a minor modification, you cannot, the neural network which is in place cannot be changed slightly, because it's a single component. You have to replace the entire thing and train it all over again. Some hand design modules are actually very, very useful, and because you cannot use it in end-to-end learning, it kind of relies more heavily on data. So we cannot use these modules. So some of these are good at solving particular tasks. They're good at what they do. End-to-end learning is a more generalized approach. So again, like when the data is limited, it makes more sense to use a specific hand design module that is made for this task. It's also very difficult to validate this approach because the architecture is very complex. So the potential number of input output pairs are they're big enough that validation becomes impossible. And validation is really important nowadays, especially since machine learning is so widespread, ubiquitous. So it becomes really important, especially in sectors like like the automobile industry for autonomous driving. So it becomes a little hard to do this when we use end-to-end learning. This is the reference I used. If you guys want to know more about end-to-end learning, this is a pretty good reference. That's all I have. I'm going to stop sharing now.
Is
Yeah.
there is there any questions or comments for this part?
I feel like this is a very important topic, especially for our research question. So one of my fellow PhDs here at the School of Information had this topic of end-to-end machine learning as his dissertation. Now he's a assistant professor at Maryland, and this is basically his field of research. This is an important topic specifically for us because we're working on online communities, and so one of the advantages of doing any kind of machine learning in online communities is that data is being generated all the time, and you're dealing with big data sets. And end-to-end machine learning is usually very helpful for big data. It's not applicable to like a small data sets that you're using for a specific purpose or to answer a specific research question. But in online communities, because that's the nature of an online community to automatically generate a lot of data over time, end-to-end machine learning has been used a lot in the literature.
Yeah.
Yeah, thanks, Iman, for the comments. Okay, if there's no questions, okay, thanks, Arian, for your presentation about end-to-end machine learning. So next will be Renbek.
Hello, can you see my screen?
Yeah.
Hello, everyone. Okay.
I have a request for you. Is it possible for you to move your microphone or speak louder? Because I have a lot of difficulty hearing you.
I mean, I'm not talking with headphones. I can just be closer to the computer. Can you hear me now?
If you speak louder. Thank you.
Is it okay? This loudness is fine?
Yeah, it is better. Thank you.
Okay. Okay, so my topic for today is deep learning with attention. Yeah, so I just saw there was like only one node, but it's such an important topic in recurrent neural networks and NLP and everything. Yeah, I would assume that we know what like the encoder decoder sequence model is, right? For RNNs and recurrent neural networks, right? So let me go over the motivation. So let's just quickly like review encoder decoder architecture. So we have so it's used for some problems such as like machine translation and also image captioning. Like machine translation, when you translate from one language to another language, and image captioning, you get an image, and you actually can try to generate what is inside the image. Yeah, so we kind of like input is kind of a sequence, and we kind of at the end we can generate another sequence. Yeah, so it consists of two parts: encoder and decoder. Encoder part is RNN, and you put the sequential input through RNN, and you get like one final hidden unit. This hidden unit you put into another RNN, but this RNN is for generating another sequence. So yeah, and so just like brief recap of encoder decoder modeling.
May I interrupt you for a sec?
Yeah.
Sorry, Jing, if you hear me, I feel like this is a really good topic for your project for the NLP algorithms you have been working on.
Okay, got it.
Continue, please.
Yeah, so And one big problem with that it's when you go very long sentences. Let's say in a case of machine translation, when you go to long sentences, at the end we just the decoder, like in encoder part, the decoder part just gets only like one unit or one vector representing the whole big sentence. And it's usually proven that just simple sequence-to-sequence modeling are failing for the long sequences, because even with LSTMs, which are supposed to like keep the memory, work over longer sequences, but it still works badly. On contrary, as attention is one of the most important innovations in deep learning for the last few years. Yeah. And to fight with long sentences, researchers came up with a technique called attention. The attention mechanism tries to mimic our thinking, because we're not like going for each word usually in turn. Sometimes we in image or in sentence we can try to focus like on different elements of the sentence first, and then based like we have like various very important words or very important things in the image, and based on that we like generate a sentence we need. So yeah, attention motivation wants to like mimic that. So instead of passing just the final hidden unit to the decoder part, we kind of pass all the hidden units, all the RNN's hidden units to the decoder part. So let's divide it. Let's review it like in more depth. So the attention, the general attention mechanism also consists of encoder and decoder part. So in general attention, there is like another type, self-attention, but I'll talk it later. But it's just general attention. So now general attention has an encoder. It's just absolutely the same as an encoder from sequence modeling, but now we're just passing not the last hidden layer, but all the other states, all the states from all the time steps. Yeah, and for decoder, most upgrades are here. So so we still use RNN cell like LSTM or G or just simple RNN, but so usually when you generate a word, you use the hidden states from the decoder to predict the next word. But now we also add, but and now we pass like all the time steps. Also, that want those all time steps to affect the input or the output of decoder at each time step after we run it through like the RNN. But there's different. But for like different inputs of different lengths, we're going to have different amounts of encoder hidden units. Like depends on length of how much sentence and how much that. Also, like how we can fix the like input dimension for that output function. One way is to add, like we can add weight to each encode, like for each time step in the decoder part, we can add weight to each encoder hidden state and sum it up. And we get a current context vector that we also were talking about in a encoder decoder part. So let's say we need to introduce a scoring function for each, sorry. So we need to introduce a scoring function for each decoder and encoder hidden states. So here's an example. So let's say encoder states just h1, h2, ht, and the current decoder state h prime t. So yeah, so we will talk about scoring function later, but now let's score these functions based on the kind of similarity or based on importance. So we're gonna have bigger score for more important vectors and less score for less important words or vectors. Yeah, so we have all the scores. We're gonna softmax them, so like normalize, so the sum is 1. And we're gonna add the weighted sum of all the encoder states, and this is gonna be our context vector. Yeah, you can see how the scoring function will work for each of the decoder states. As you can see here, we score each encoder state and apply a softmax function on it in order to normalize the scores and add them up. Yeah, so let's review the main part of the decoder is that like the scoring function. So there was two major types of attentions were introduced with like two major papers on attention. They introduced attention. So those are additive and multiplicative attention. Additive, also called Bogdanov attention, based on the first author of the paper that introduced additive attention. And multiplicative attention, also called sometimes Luhmann attention, also based on the first author. Yeah, so one major difference is between them. So in additive, we use for each decoder time step to calculate the generated word for this time step. We, instead of using current decoder hidden state for the context vector, we use previous decoder state for the context vector. But in multiplicative, we use current decoder state to calculate the current context vector. Yeah, you'll see in those. So let's go over first multiplicative attention. So multiplicative attention also divided in three parts. It's dot attention, general attention, and concat attention. So the first type of multiplicative attention is the dot attention. This is easiest option to implement and to understand. It's just based on dot similarity. Geometrically, the dot product depends on the angle between two vectors, and if angle of the cosine of the angle, and if cosine of the 0 is like 1 and the biggest, like if the two vectors goes more far each other from far, the dot similarity will be less small and less small. And if vectors are similar, the dot similarity will be very big. Yeah, for example, like if the two vectors are orthogonal, the dot similarity is like 0. Yeah, so now we're gonna score all the like hidden units from encoder, and we're gonna just talk the vectors that are similar to current decoder vector to check which are kind of important. One disadvantage is for that like the scoring function is fixed and it's not changing over learning, so it doesn't like it's not it doesn't utilize any kind of learning. So yeah, because the other attention functions kind of also implement learning. So from here we can go to concat attention or to general attention function introduced in a long paper. So this is very similar to dot attention, but also adds a kind of learning aspect to it. So first, before taking a dot similarity, we kind of take the each encoder state, as you can see here, and we pass it through a just usual multi-layer perceptron, the just usual dense layer, and then we try to check for similarity. In this case, it will kind of tries to learn. So this function is subject. This weight is subject for learning, also for backpropagation and gradient descent. It also kind of learns over time which vector are supposed to be important for this decoder state. Yeah. So and another is concat function is the last one. Yeah. So here you can see the formula for it. It's first is concats the current decoder state and current hidden state, concatenate together, run through the multilayer perceptron with the activation function tank, and also uses another neuron like multilayer perceptron with 1 to get the final score. You can see over here the structure of it. So you see over here, we concatenate it, we run through a neural network, just dense layer without any activation. We apply tank activation function, and we kind of like the last hidden unit of the neural network for just one number, which is the score. Yeah, so that adds up all the multiplicative attention types. Let's go over additive background attention. Yeah. Over here, you can see instead of kind of multiplying, we kind of add over here. So this is the formula for. Also, let me forget. So this is this structure is also helpful for actually implementing the function in Keras and TensorFlow because it's divided into layers, and you can just like apply layers from Keras and TensorFlow. You have the concatenate function and everything. And the same over here also. So yeah, it's very similar to concat function, but it doesn't concatenate the input states. It's like runs both of them through the neural networks and sums up, and then applies the activation function, and then the final hidden layer. Over here, you can see the structure. Like first we run this through a neural network, we run this through a neural network, we get this output of the neural network, we sum them up, we apply the activation function, and we get the final score at the end. Yeah, and to like show you on a let me show an example how attention works. Say, so this is example of how would attention work for neurotranslation example. Yeah, so in this case, we're translating the word from how are you from English to Russian. How are you in Russian would be как твои дела. Yeah, so let's say first we run the encoder states. So let's say how are you, we run the encoder states and encoder states for each of the words, kind of time steps, H1, H2, H3, H4. Now we use some initial hidden state for the decoder. So this is a starting starting point. It's not a word, it's just starting point. So it's like starting token. It goes through the embedding layer that each word. So in order to turn a word into a vector representation, yeah, then it's the goes to the RNN cell, which can be simple RNN, LSTM, GRU, or anything other. And here's the decoder state. So we use this decoder state and and all of those to calculate this context vector. And so now using this both of those, we put them into another neural network to get another final next word. So it will be как. We take this word, we push it back and do the same thing until we get to the kind of end token. And here we go, our translation. Yeah, over here you can see the structure of how it might work, how it works with attention. Yeah, so yeah, I put the references for those the first two, one of the major papers on the attention. Is there anything I forget to cover? I guess no. Yeah, the attention leads later to self-attention and leads to transformer models that have over a lot better performance than usual STM and on the longer sequences and even shorter and even faster. Yeah, that's the end of my presentation. Do you have any questions?
Thank you. That was great. And in previous sessions, I had difficulty hearing you. This session, it was great. I understood almost everything. Thank you.
Okay, thanks, Renback, for your presentation about the attention mechanism. I think that is a really good job. So, I think we have all of our presenters today.
I want to present my research idea because in the previous meeting I failed to describe it.
Oh yeah,
if you
sure.
don't mind, if you have time.
Go ahead.
Okay, thank you. Do you see my screen?
Yeah.
Thank you. Okay, so I'm planning to talk about music style transfer. Shortly, music style transfer means combining two different styles of music into a new one. Now I will describe generally what is style transfer. Style transfer is applying the style or characteristics of a new image, video, voice, or music to the input one. Image style transfer was quite successful. Nevertheless, the same can't be said about other areas. So I have here a link for the Google Colab notebook, which shows neural style transfer. Here we have two images. The first one, in the first one, you can see the sea turtle, and second one, shows us the picture, the Great Wave of Kanagawa. And we use this image as a style, and as a result, we get a new image, which is styled according to the second image. I think this would give you a good understanding what means neural style transfer in case of images. And here you can scroll down and see some code snippets and descriptions, and this would give you a better understanding how style transfer works in case of images. So what is the purpose of music style transfer? It would help us to create covers for the songs. It will bring pleasure to humans. It would help us to understand the key characteristics of the music. We will be able to create new music that is both human-like and creative. And I have here a quote from the research paper. One can only imagine the amount of effort that goes into arranging an entire symphony based on a comparatively simple rock song. Domain transfer systems could significantly accelerate this process or even automate it completely, which would let us enjoy music that generally has not been feasible to create on a large scale. Here I have put the challenges associated with music style transfer. The term music style is very difficult to be defined, and music has multi-level and multimodal representation. So on this note, I describe different representations of the music, score representation, performance control representation, and sound representations. Now I would give you understanding what these terms mean. Score representation. So this is a high-level representation of the music, for instance, like lead sheet and chord chart and so on. In case of performance control, we have MIDI piano roll, and here each note is encoded by its pitch and dynamics. And the last one is sound representation, which is the most low-level representation from these three. And here we use spectrograms and waveforms. And I have here a quick summary of distinctions and differences between these representations. As I already explained, we have different music representations, and we use different models for those representations. So timbre style transfer is used for sound, performance style transfer is used in case of control, and composition style transfer is used for the score. So I have here more precise definitions for them, and I have quotes from one of the research papers, which I included in the references. So this means to alter the timbre information in a meaningful way while preserving the hidden content of performance control. In case of performance style transfer, this applies to performance control representation, and it means to alter the control information in a meaningful way while preserving the implicit score content. So to give you an example, a good or a successful performance style transfer would manage to style, for instance, Bing Crosby song into Frank Sinatra song, or George Harrison song into Jeff Lynne song, or something like that. And lastly, we have this composition style transfer. Composition style transfer means to preserve the identifiable melody, contour, and the underlying structural functions of harmony while altering some other score features in a meaningful way. And as an example, I have a Mozart piece of music, which is called A Diraiji Maman. And Mozart used here a seme which was not created by him. and created variations of it. And I can play some part of it for you. And a very famous Chinese composer, pianist Lang Lang, explains this, and you can check it. And I also found some previous attempts to create style transfer, and here is a demo. I can, for instance, load this piece of song. So here we have an input. I would just play part of it. Here we have style input. And after applying this style, we get this one. In case you would be interested, you can check this demo and play with it. So this was what I wanted to share with you.
Yeah, I think that is really interesting.
Thank you.
Yeah, and is there anyone has questions or comments?
Just about some of your notes. First of all, it was a really interesting presentation. Thank you. And so you correctly use idea notes for presenting your own ideas, like the type of the note that you proposed was idea, which makes a lot of sense. The only point is that in some of your notes, I saw you have links and like citations. For putting links to external websites, please only use reference notes. And wherever you need to refer to them, just cite those reference notes under the note.
Oh, thank you. I'll take that into account.
Thank you. So has anyone looked at the papers that I posted on the channel? Or did I? I think I did post the papers to the channel, right?
Yes, I saw your editions of our document.
Yeah, so sorry, I made a mistake. I only edited the document. I didn't post them in the channel. So if you look at if you open detailed research plan file, I added a few new papers to this file. If you're interested in working on the third research question, these are good papers to start with. And one of them is basically using deep reinforcement learning, which was a little bit discussed today. So if you're interested in just continuing the discussion about deep reinforcement learning, that can be a good paper to start with, and you can just start summarizing in One Academy. If one person has started summarizing any of these papers, it doesn't mean others cannot do that. So multiple people can summarize each of these papers at the same time on One Academy. The only point is that if you start, if you want to add a new node, you're not supposed to duplicate any nodes on One Academy. If someone else has already added that node, you can propose an improvement on it, or just vote on that node. Don't propose it again. Any questions about these papers or the research question or anything for me?
Okay.
And if you find other helpful papers related to this research question, please feel free to add it to the end of this section of the document, just in this list.
Yes, I'm also noticed that Robin is planning to prepare for the deep reinforcement learning, but I think she is going to just introduce some fundamental concepts and how that works in general. And you are still feel free to read through the papers even proposed, even shared in our document, and share anything you learned during our meeting. Yeah. Okay, so I think that is all the stuff for today's meeting. If there is no any other questions, you can feel free to leave.
Thank you.
Thank you.
Goodbye.